Hey guys, we are doing another form of an integration technique today. It's called partial fractions. These are your notes for 7-5 day 1. And so far we've done U substitution, which undoes many instances of the chain rule. We've done integration by parts, which undoes many instances of the product rule. And we've done separable equations, which undoes implicit differentiation, many instances of implicit differentiation. Partial fractions undoes largely, it undoes more than that, but largely partial fractions undoes logarithmic differentiation, which is a technique to avoid quotient rule when doing a derivative. So in a roundabout way, partial fractions undoes quotient rule. The thing is, you'll often get your answer as a logarithm because you're seeing how it that way you can see how it undoes the logarithmic differentiation. It's harder to see how it undoes the quotient rule. Anyway, let's get started. Before we get started, I have to review some algebra techniques with you and some basic calculus techniques. So real quick, I would call these rational functions because you've got like a polynomial in your denominator. And if I asked you to add those two fractions together, you would say, oh, okay, well, I guess I have to get a common denominator. True. So you know that this is a binomial, it can't be separated. This is a binomial, it can't be separated. So your denominator needs to consist of one of each binomials. So in your first fraction, you're going to need an additional binomial of x plus 4. So we're going to go x plus 4 over x plus 4. And your second fraction needs an additional binomial of x minus 7. And what I usually tell you is don't multiply out your denominators, only multiply out your numerators. Don't multiply out your denominators unless you have a really good reason to do so. So I'm going to go distribute the 2x plus 8 over that binomial times that binomial plus 5x minus 35 over, again, that binomial times that binomial. Now that you have common denominators, you may combine your numerators, and I get 7x minus 27 all over right? Or another way you may see this kind of result is with the denominator multiplied out. So you might see it as 7x minus 27 over x squared minus 3x minus 28. So keep in mind, when you see something like this, called a rational function. You've got a polynomial on top and some other polynomial in the denominator. Just know that this could very well have been the result. This could very well be the result, the complicated result, of adding two simpler fractions together in the first place. And I know that you've gone from here to here quite a few times in your high school, 4 years of high school. But I don't believe you've ever gone from here to here that I know of. Okay, the other thing I want to show you is just a reminder of some kind of simple calculus. You all know that the antiderivative of 1 over x dx is natural log of the absolute value of x plus c. When this is a simple variable, you may use this simple antiderivative. What if this is messy? For example, what if this is 1 over, and I'm not talking super messy, I'm just talking kind of messy, 1 over, I don't know, 2x plus 9. If you say that your answer is natural log of absolute value of 2x plus 9 plus c, it's wrong. Because this is messy. Technically, you would need to use u substitution. So let me show you the u substitution really quickly, and you'll be like, oh yeah, I've got that. I don't need to show all that u substitution every time I do one of these. You'll get the shortcut here in a minute. So if I were doing u substitution, I would say that u is equal to this. And I would say that du is equal to 2 dx. Right? So I just did a quick rewrite. I rewrote the exact same thing, but I color-coded it so that you can see my replacements. This is definitely going to become a u. I want this to become a du, but right now it's not equivalent. You're missing a 2. So throw a 2 on. Keep it legal. Now you've got 1/2 1 over u, and all of this matches this and becomes du. Aha. Now, your answer is 1/2 ln absolute value of your original u. So, I know your temptation was to just say, just to use that process on this one, and you can't. Why can't you? Because there's a 2 in front of the x. It's a little more complicated. How would you uncomplicate it? By using u substitution. Remember, you would need an extra 2, so throw a 1/2 out there. So I think that you can, from now on, go straight from here to here. Y'all are smart like that. So here we go. Back to the beginning. If I asked you to integrate one of the 2 problems, and you had a choice, which would you rather integrate? So here, my first thought, like right here, I'm thinking, oh, maybe u substitution, because that's a quadratic and that's linear. So, ooh, this could be my messy, and that could. No, that's not going to work. U substitution is not going to work. Integration by parts? No, I don't have 2 things being multiplied together. Separation of variables? Nope, there's no y's there. Okay, so now we're on to like the 4th technique of integration. So what we're going to do is we would choose this one. Because for these, I would maybe separate them into 2 of their own separate integrals with subtraction. So I would do the integral of this piece minus the integral of this piece. I would pull my 5 off because that's just a constant. Get that out of the way. Then you would be integrating 1 over 2x minus 1. I just showed you how to do that easily. This one, pull the 2 off. Integrate 1 over x minus 3. That's easy. Okay, so here's the thing. It's our job to get a complicated rational expression to look like 2 simpler fractions that were added together to create that. Now, there are some requirements up here, but I disagree with these requirements. The requirements said P and Q are polynomials. Okay, yeah, that's true. It says your top degree has to be less than your bottom degree. I don't know that I agree with that. The product does need to be able to be written as factors, but I don't think they have to be linear. And I've discovered all this when I'm working out problems using partial fractions. So who knew? So let me just start with the process. We're going to take this complicated rational function, let's break it down as a sum of simpler rational functions. So here's what we're going to do. Here we go. Write the rational function, top left corner of your space, and go ahead and factor the denominator. So let's see, I know that has to be a 2x and a 1x. Has to be 3 and 1. Where do I want them though? Do I want a 3 and a 1? No, that makes 5. A 3 and a 1, that makes 7. That's where I want them. 1 minus 7, okay, so minus minus. There we go. All right, so I have it factored. I think that this was equal to 2 fractions added together. I think that the denominator of one of them was the binomial 2x minus 1. And I think that the denominator of the other one was the binomial x minus 3. And I also think that there was some constant on top. There was something up here, and there was something probably different up here. So I will call this some constant A and some constant B. Okay? Now, and I think that if I added those together, I would get that. So how would I go about adding these together? Well, I would have to get a common denominator on each piece. So this one would need an x minus 3. So I would have to go x minus 3, x minus 3. The other one would need a 2x minus 1. 2x minus 1, 2x minus 1. Now, here's the thing. This one fraction is equal to these two having been added together. So check this out. See this denominator? Isn't this denominator the same all the way across? So if my denominators are exactly the same all the way across, all you have to focus on is working with the numerators. So let's just work with the numerators. Let's like ignore the denominators for now, because we know that we've got those matching all the way across. Let's just work on setting up our numerators to make sure those are equal. So I would write x minus 13 equals A times the quantity plus B times the quantity. And now we need to solve that for A and B. Slight problem. If I try to solve for A, this is an equation with 3 variables. I can't do that. Same for B, an equation for 3 variables. I can't do that. However, this is going to be so cool. This whole thing right here is true for all values of x. It's true for all values of x. Because whatever you plug into here and whatever you plug into here, these are the same, which you'll see in a minute that they are, they would be equal. It's true for all values of x. So, you ready? Let's say, I'll do B first. Let's say that I would really like to find the value of B. Well, what's in my way of that? 2 things. There's an A that's an additional variable that's really in my way. And there's also an x scattered throughout that's an additional variable that's really in my way. But since this is true for all values of x, is there, so yeah, you really want the a to go away, but how about this? Is there an x value that you could choose that would wipe out all of your extra variables and you could just solve for b? I think there's an x value that you can choose that will wipe out all your extra variables and you can solve for b. And I think that x value is positive 3. I'm going to let x be positive 3. Here's what it looks like. Sub in 3. 3. I subbed in 3 for x. This is negative 10. This is gone. I can solve this. That is so cool. B is negative 2. Do it again. I think, let's focus on A. We want to solve for A. I think that there is an x value that you can sub in all 3 places that will make all of your extra variables disappear. And I think that would be positive 1/2. So I'm going to say let x be positive 1/2. Here's what I've got. I hate mixed numbers. That's better. Oh, dang, I'm out of room. Let's see. Do I have any extra space? Oh, I have 0 extra space. It says then find the antiderivative. Well, I can write it tiny. So here's what I'm getting ready to do. I am going to change this to make it look like this because we did just come up with our 2 fractions. So I'm going to write, I'm doing the, let's see, let me divide this off a little bit. So my original rational expression breaks down to 2 smaller rational expressions. One of them was a over 2x minus 1. A over 2x minus 1. And b, oh, that should be a minus, over the other one. What was the other one? X minus 3. I'm gonna separate into two integrals. I'm gonna pull the 5 off. 5 antiderivative 1 over minus pull the 2 off, antiderivative 1 over this one's going to be an easy one because there's only a 1 in front of that. This one's going to be one where you're going to have to use that shortcut that I showed you at the very beginning. So I would call this 5 times a half ln absolute value 2x minus 1. And then I'm going to do the plus c at the very end. Minus 2 ln absolute value x minus 3 plus c. Alrighty, let's try the next one. The next one, the good news is the denominator can be factored, but you're going to have a really hard time with this quartic function. If you try to separate your variables and you got an a up there and a b up there, that's going to be nearly impossible. So, I guess really what we're striving for here is turning this rational expression into something that meets these requirements, maybe. And in order to do that, I'm going to actually divide my two polynomials. Oh my goodness, it's been a while for you. I'm going to divide my two polynomials. So I'm going to go x squared minus 1 into 3x to the 4th. Oh, wow. You thought you would never, ever use this again, I bet. What's it take to, what do you have to multiply this term by to get 3x to the 4th? I need a 3x squared up there. 3x squared. Now multiply. 3x to the 4th minus, I'm going to line them up, 3x squared. And don't forget that we are subtracting. That's gone. That never was there in the first place. A negative minus, okay, so this is going to be positive 3x squared plus bring down the 1 and I need to multiply that by positive 3. 3x squared minus 3 4. Okay, so I ended up with a remainder of 4. Okay, so after doing this division, I'm going to rewrite my integral as the result of what I got when I did my division, because they're equivalent expressions. I did the division. So those two things divide and give me a result of 3x squared plus 3, plus I have a remainder of 4, and remember how you write your remainders? You do plus 4 over what you were originally dividing by. Okay, now this term is going to be super easy to integrate. This term is going to be super easy to integrate. This one is not. We need to work on this term getting it to a place where it is able to be integrated. So I'm going to just highlight, this and come over here and say, let's work on it. So 4 over x squared minus 1, right? So over on this side, I'm going to work on breaking down that rational expression. I know that my denominator can be factored, so I went ahead, oh, hang on. I jumped ahead of myself there. Slow down. All right, so the bottom can be factored. So I think that I did have a fraction with this binomial, and I had a fraction with this binomial before I got common denominators and added them together. So, this one is going to need an x minus 1. Hold on. A, B, my bad. This one is going to need an x plus 1. And then since all three denominators are the same, you are going to focus just on the numerators. True for all values of x. Choose an x that you would like to sub in. See if I did that right. Subbed in -1, subbed in -1. There we go. So this is 0, that's gone. And then to work on finding b, I'm going to go back up to the original. I think I would like x to be +1 to help me find b. So, -2 is what's on top of my x plus 1, and +2 is what's on top of my x minus 1. So, let's go back up here to where we were getting ready to try to evaluate this integral. So I think what I'm going to do, I'm going to go ahead, just to kind of save some space, I'm going to go ahead and integrate this piece, get it out of the integrand. I'm going to integrate this piece, and I'm going to work on integrating this piece. So the antiderivative of 3x squared is raise it and divide. The antiderivative of 3 is 3x plus, now I have the integral of, instead of this, I forgot what I have, negative 2 over x plus 1 plus positive 2 over x minus 1. Pretty sure that's what I have. It might help. Okay, so we changed this fraction to these. This may help you, this may not, I'm not sure. I went ahead and split these into two integrals, and at the same time as I was splitting them, I pulled the constant out to the front. Pulled the constant out to the front. I love getting all those constants out of the way. They don't confuse me. This becomes a very simple antiderivative. There you go. And one more thing before I let you go. Another way to write this is, let's see. Do I want to show you that? I think I do want to show you that. You could pull the negative 2 out. That looks like a 2. I think it should have been a 3. X cubed plus 3x Okay, I'm going to, I want to work on condensing these logarithms, okay? So they both have a 2 in front of them. I'm going to factor off a positive 2, which is going to leave this a negative log and this a positive log, and then I'm going to reverse them so that I have log of x minus 1 minus log of x plus 1. Pulling off a 2, switching them around so that there's a minus sign. ln x minus 1 minus ln x plus 1. And the reason I did that is so that I can condense these with division. I gotta be careful because my absolute value symbols look like 1s, and that's really dangerous in this problem. Okay. And guess what? The derivative of this, when simplified, equals that rational expression. Pretty cool.